Hi, thank you for tuning in to the talk. I'm Samyak, and I'll be presenting our work Global Convergence of SGD for Logistic Loss on two-layer neural networks, which recently got accepted into TMLR. This is joint work between Pulkit Gopalani, me, and Professor Anirbit. This talk will proceed in the following manner. First, I'll start by introducing the problem. Then we'll review some existing literature and techniques and provable guarantees for gradient-based neural network training. After that, we'll see a certain class of interesting functions called Villani functions in our neural network setup. After that, we'll see our proof of SGD convergence for any depth to loss function. And finally, we'll discuss some potential avenues for future research. So let's begin. The neural landscape makes optimization very hard because training neural networks requires minimizing a high-dimensional non-convex loss function, a task that is not in theory but sometimes easy in practice. SGD and its variants, despite being fundamentally simple algorithms, have been surprisingly and widely successful in training deep neural nets for various data and various sizes. The success of SGD, despite the complex non-convexity and also non-differentiability of the neural landscape, largely remain unexplained. And in this presentation, we shall establish, likely for the first time, that SGD can converge the global minimum of certain neural loss functions at arbitrary width and data. To put this in context, we'll do a quick review of related works. An active line of research explaining the optimization in neural nets has been the NTK or the neural tangent kernel approach, where the key idea is if epsilon is the target accuracy, then at a fixed depth, many neural networks become effectively linear in their weights for width scaling as polynomials in 1 over epsilon. The best case known for this proof is by G and Kaligarsky, who use polylogarithmic width for the same logistic loss setup as we consider in our work. Clearly, this width regime is unrealistically large and can do careful studies of the individual data used in any SGD update and affect predictions at other data and see that this is very different dynamics between real nets and this limit. If one is interested, they can look into the works cited at the footnote for the idea of local elasticity of deep learning by some of the current co-authors. Another recent prominent line of research for analyzing SGD for neural nets is the mean field approach, where the key idea is to formulate the study of the neural weight dynamics during training as a study of the dynamics of probability distribution on the neural net weight space. This replaces a non-convex optimization problem in finite dimensions with a convex optimization problem in infinite dimension, but clearly such analysis is only meaningful for infinitely wide nets. These are some milestones in provable guarantees for multi-gate depth to neural network training. In summary, it seems that it has remained an unresolved challenge to show convergence of SGD on any neural architecture with a constant number of gates while neither constraining the labels nor their data distribution. Our story begins with the work of Pinchy, Wei Su, and Michael Jordan, where they analyze the effect of learning rate on SGD by studying the corresponding continuous time limit of the stochastic differential equation. Formally for an objective function L bar, where W denotes the weight matrix, the mini batch SGD update at the gate step is given by the following expression. Here, the indices represent the index of the mini batches. Given the above step sizes of the SGD update, the authors prove that its iterates are close to the following SDE, and the density of the weight matrix evolves according to the following Fokker-Planck-Smoczarski. The FPS PD, they showed that when L bar is a Villani function, which will be defined in the next slide, the solution to the above FPS PD converges to the following Gibbs measure that approval guarantees and the conversion rate. The idea of Milani functions possibly first occurred in Cedric Milani's 2000 monograph Hydrocoercivity. And we define Milani function as follows. A map F from power D to R is called the Milani function if it satisfies the following conditions. It is infinitely differentiable or a smooth function. As we go towards infinity, the function will blow up to infinity. And the integral of e to the power minus 2f over s for all s greater than 0 must be finite. And finally, as we go towards infinity, the negative of Laplacian of f plus 1 over s into the square of the norm of the gradient of f must go up to infinity. Any function that satisfies the first condition is said to be confining. Key to the argument of the paper for getting the non-asymptotic convergence is the fact that the Gibbs measure corresponding to a Milani function satisfy the following Poincare type inequality. In simple words, if for a Milani function f, and for any given s greater than 0, we define the Gibbs density mu of s as e to the power minus 2f over s divided by normalization factor. Then this Gibbs density satisfies a Poincare type inequality. That is, there exists the lambda, which is determined by f, such that for all infinitely differentiable function to power d, we have the variance of h with respect to the Gibbs density is less than or equal to s over 2 lambda s into the expected value of the square of the norm of the gradient with respect to the Gibbs density. Our analysis depends critically on the main theorem or the theorem 1 of Xi et al., which goes as follows. If L bar is both confining and Milani, then there exists a lambda s for any s greater than 0, which we call our learning rate, such that for certain functions epsilon strictly greater than 0, which is strictly increasing in s, and a function d, which is non-negative, where rho initial is the initial distribution, we have the following exponential convergence of the expected excess risk as follows. And so it's outlining the proof of the above. We treat the expected value, the for loss function as at infinite steps as the expected value of a loss function, where the weight matrix is sampled from the Gibbs density. This is justified by the following convergence theorem, which we count as the first step of the 3 main steps to taken to prove the main theorem. Now, theorem 1 states that if L bar satisfies the confining condition, and if the initial distribution of the SGD belongs to L2 of 1 over nu, then the unique solution rho of the FP's differential equation of the SDE converges in L2 1 over nu to the Gibbs invariant measure nu. We note the following decomposition of error. The next 2 steps will mainly involve obtaining upper bounds on these 2 terms via the following theorems. So our step 2 will be bounding the first term in this decomposition of error, and it's the proposition 3 of Xi et al. States that for L bar being confining in Milani and for any s greater than 0, there exists a lambda s such that we have a function c, an increasing function in s, and for all t greater than 0, we have the modulus of our first error term is less than or equal to c times e to the power minus lambda st into 1 over nu s norm of rho initial minus nu s. Here, this 1 over nu s norm measures the gap between the initial distribution and the stationary distribution. Our third step would be proposition 3.2 of Xi et al., where they quantify the excess risk at stationarity as for all s greater than 0 and s belong to capital S greater than 0 and s belonging to 0 to capital S. There exists a function A such that the excess risk at stationarity epsilon of S is equal to the expected value of the loss function is the number of steps into infinity minus the optimal like the infimum value of a loss function, which is less than equal to this function A into S. And combining these two bounds obtained in step 2 and 3 respectively, we are led to the key upper bound stated in the main theorem of Xie with an appropriate definition of the function t therein. Now, in the paper, the authors commented some loss functions used for training neural networks might not satisfy this condition. So we'll now start defining some key components of our work. We begin by considering the following setup. We define a two-layer neural net function which maps r to the power d, a d-dimensional real vector to r with trainable weights w, and fixed weights a, an activation function sigma, and the data in d-dimensional real space as follows. And for n data tuple and positive lambda, the Frobenius norm of the Frobenius norm regularized loss we consider is the following function. Now, consider the following set of neural nets. Let the activation function be bounded, infinitely differentiable, L Lipschitz, and L sigma prime smooth. Further, the first and the second derivatives of sigma should also be bounded. Some common example of such function would be, such activation function would be tanh and sigmoid. We can relax the boundedness assumption, but this would come at the cost of forgetting the discrete time convergence. Now we begin with discussing our proof of SGD convergence for any depth to appropriately defined loss. So our primary result in our paper will begin with the following theorem on the bounds of on error for arbitrary initialization. That is, for activations considered, the loss L bar is G-lib gradient Lipschitz, and there exists a lambda critical, lambda c, greater than 0, such that for all lambda greater than lambda c, the loss function is a Villani function, and for all t and epsilon greater than 0, there exists constants A depending on L bar, and B depending on T and L bar, and C depending on S and L bar, such that with SGD at constant step size, defined as follows, we get the bound on error as epsilon plus C into the gap of stationary distribution, the Gibbs measure, into e to the power minus S into lambda S to K. Here K denotes the number of steps taken. In other words, or in simpler words, when using neural networks consisting of just one layer of sigmoid tanh weights, regardless of the data and network size, and employing SGD with a critical regularization on logistic loss, taking small enough steps, the algorithm will eventually find weights that make the expected value of the regularized loss close to the minimum value. However, the suboptimality with respect to the global minimum is parametric in the distance between the initial and the stationary distribution of the underlying SDU. A lemma derived from the aforementioned theorem, global convergence of SGD on arbitrary data and width for logistic loss. We start by continuing the same setup as the theorem, but with the new step size defined as follows. And omega naught, the initial weight sample from the distribution L2 1 over nu s. And nu s is the Gibbs measure. 2 into C into the gap between our initial distribution and Gibbs measure, less than or equal to epsilon into e to the power lambda is into t. Then we get the following bound on error. Here K denotes the number of steps taken. This lemma is a particularly interesting case of the main theorem. Notably, if we ensure that our initial weights are sampled from a distribution which belongs to a specific class of distributions, then using the same setup as the above-mentioned theorem, the network will eventually converge on weights that bring the expected value of the regularized loss within epsilon of the global infima of the loss value within O1 over epsilon steps. For intuition about the value of the regularizer, consider sigmoid activation and suppose that we normalize the data of with respect to the maximum of BFX and the layer weights A, such that BFX into norm of A is equal to 1. Then we obtain that our lambda C is equal to 0.03125. The critical value of regularizer comes from the following condition of being a Milani function. It's important to note that the critical value of the regularizer that is needed in our analysis does not depend on the size of the net. It also becomes proportionately small as the norm of the fixed second layer weights decreases. The Gradient-Lifshitz condition on the loss function is required by the standard theorems for converting the continuous time convergence achieved through Villani functions to a discrete time convergence result. The loss function L bar for softness, the smooth inversion of Rayleigh, does not satisfy the smoothness condition, but the SDE shown earlier still probably converges to the global minima with softness. We define the softness activation function as the following. So a result for softness nets goes as follows. For any small enough step size, lambda greater than lambda C, which we define to be 0.03125, obviously with data and last layer norm being normalized in appropriate ways such that the product of their norm must be 1. And for time greater than 1 over lambda into log of 2c into the distance between rho initial and nu s with respect to 1 over nu s measure over epsilon, we have that the expected value of loss function at time t minus the minimum value of that loss function it can attain is less than epsilon. This is linear time convergence. And we run the following experiment on MNIST to classify our experimental data into 2 digits. In the experiment shown above, we perform binary classification experiments on the digit pairs 2 and 7. In our experiments, the elements of the trainable weight matrix W0 of dimension 784 is initialized on the standard normal distribution, and so is the fixed outer layer of dimension 1/12, which was then rescaled by the largest data norm to ensure the value of the C is equal to 0.03125. And the model was trained for 100 epochs with a mini batch size of 3,000. We measured the test accuracy of classification as the downstream metric of measuring the goodness of training. And at the end of training, we achieved an accuracy of 90%. In analogous regression setup, but some work was done by co-authors Pulkit and Anirbit, where they obtained similar results. They obtained the following test laws for different values of a regularizer. And to the best of our knowledge, this is the first result showing global convergence of SGD on neural nets without any assumptions on the data or the number of gates. Naturally, we can ask, could the Villani function idea be a general method to prove the SGD convergence on various other neural loss functions? Can we characterize the lambda S or the Gibbs measure of neural nets? This becomes a relevant question now that we can establish that for certain neural losses, Poincare constant of the Gibbs measure is the time scale of the SGD convergence. That's it for me. Thank you for sticking around and hopefully you enjoyed. Thank you.